Hi guys, I had a LED lamp break down the other day, and since I have several of these LED lamps and drivers, I wanted to make a little bit more of a deeper analysis to make sure I can solve future problems when they arise. So let's start looking at some basics and a schematic walkthrough. LED drivers are either isolated or non-isolated. Typically, the standalone drivers are isolated, whereas the LED lamp integrated drivers are non-isolated, which saves you an isolation transformer and cost. In this case, the voltage rating is 230 volt, and this has a secondary side output of 230 milliamp at the maximum voltage of 35 volts. Looking at the driver board, we have the mains side, the primary side, and the secondary side. And between the primary side and the secondary side, we have the isolation transformer and the isolation barrier. Looking at the schematics, again, same kind of visualization with the main side, the primary side, and the secondary side where we connect our LED light. And if we follow the current path through here, we start down through F1, the common mode choke, the line choke, L2, up and down through our bridge rectifier, through the current limiting resistor R1, the differential mode choke, continuing through our isolation transformer and down through the main switching MOSFET Q1 and then down to the control IC. And the control IC here is the operational principle is primary side current sense. That's how it senses and calculates the secondary side current. So it goes through here, the shunt resistor, and then back through the bridge rectifier, down through the line choke L3, the common mode choke, and finally through a fusible resistor 33 ohm. The current flow on the secondary side here from the LED light seen through the isolation transformer, the rectification diode, and then down again and back to the LED light. Pointing out some key components, we have the Q1 main switch, the isolation transformer, and the electrolytic capacitors here, which are the most prone to failure in LED drivers. Below here we have the control IC, the bridge rectifier, and the secondary side rectification diode. So, troubleshooting and some common failure modes. Most of the time, the typical failure for electronics is an open circuit. Sometimes it's a short. We also see degradation and component drift, sometimes causing product behavior which is not expected, like a flickering light. But eventually most failure modes lead to an open circuit because of the excessive heat from the higher current flow fuses the component. A lot of these failures come from mechanical factors like thermal stress, heat, or thermal cycling. We could see vibration, not so much in consumer electronics though. And for the indoor consumer, the thermal cycling might not be the most stressful factor because we typically thermally cycle between room temperature and maybe 50-60 C. So here it might just be the heat. I would say the combination of low-cost designs that you have in consumer electronics with poorly rated components and maybe unforeseen customer use cases, or that the LED driver in this case is placed so the power dissipation is difficult. You simply cannot get the heat out. This can cause premature failures in these devices. I normally start the troubleshooting with the ABA test. In this case, I tested the LED driver with a different LED lamp and saw that I didn't get any light. And then I tested the LED lamp with a different LED driver and could see that the lamp worked, which means that my LED driver did not work. Then I follow the power path and I check for abnormalities with a multimeter, which I will show you on the next slide. Sometimes you need to do more detailed troubleshooting with the power connected using an oscilloscope, but I only recommend this for trained professionals. Following the current path, I would check the fuse for continuity, the common mode choke for continuity. I would check L2 for continuity. I would make diode measurements on the diode bridge to see that that is correctly and intact. I would measure the ohmic resistance on R1. I would measure continuity on L1 and measure continuity through the primary side of the inductor. I would check if the MOSFET is shorted, if I can measure the body diode with a diode measurement, and I would measure the resistance over the shunt resistors here, make sure I have the right resistance here, none of those have burned. And following the path out here, I would measure also L3 for continuity to the common mode choke and check that my fusible resistor here has 33 ohms. On the secondary side, I would measure the secondary side of the isolation transformer for continuity. I would make a diode measurement on D1, measure the capacitance on the electrolytic caps here, which are one of the most prone to failure parts on a LED driver. Also, Q2 here can be checked for short, and also it could be good to measure the diode drop of the body diode here. In my case, I could see that L2 was open, and since I drew the schematic, I could also see that R6 was open, and this is probably a secondary failure. When L2 opens, R6 probably takes a higher current than rated and fuses. So I made some replacements here. So before we had these line inductors here, L2, L3, I swapped these for same value but a little bit lower resistance line inductors. I also swapped R6 here from a 0805 to a 0603 smaller package resistor, but should be okay because it should not take any significant current. I did break FR1 during testing here, so I had to replace that also with a resistor. Sometimes it's good just to validate and check your solution. Is it robust enough? You could typically do this just by plugging in and see if it works for a sustained amount of time. I choose here to do a little bit more. I used an infrared camera here to understand the heating picture and to understand if the components I replaced got too hot. So here are the line inductors I replaced. They are in this bottom part here, and we can see that most of the heat is dissipated in L1, C3 and D1, and the components I placed or replaced, they all seem to operate rather cool. So this looks promising. Thanks guys, I hope this helps you with your troubleshooting, and good luck. Always think about electrical safety. Thanks guys, appreciate it.